Computing conditional probability from contingency table. We recall what is conditional probability. Conditional probability is a measure of the probability of an event occurring given that another event has already occurred. We use this formula to calculate conditional probability. And this formula can be understood when you look at this diagram, the Venn diagram, where we have the sample space, then the sets A and B. So when we say the probability of A given that B has occurred, that means we have reduced the sample space to B from S. So as such, this probability that we want is like we are looking at the stripped area. That's the probability we want to find. So as such, we simply say probability of this intersection over probability of our new sample space. Note that conditional probability restricts or reduces the sample space. Like I've already said, to say we are working with our sample space being the set B. Also, we should remember that conditional probability can be calculated from information presented in contingency table. Now, what is a contingency table? A contingency table is used to record information or data concerning the relationship between two or more categorical variables. That is, this is a contingency table, and I have 4 variables. That is A1, A2, then B1, B2. As we look at the variable A1 and A2, they have their values in the columns. The B1 and B2, they have their values in the rows. So that now if I consider A1, the number of elements in A1, we are simply saying you add A and C, that is the total. For A2, we have B plus D, that is the total. Then from there, if I now consider B1, the total in B1, I add A and B, so this is the total. B2, C, and D to get this total. Then what is important now is to try to get the number of elements in the whole set. That is to say, if I add these values or the totals of B1 and B2, they should give me the total. If I add the totals of A1 and A2 should also give me the same total. So I've equated this total to N so that I'll work with N as the number of possible outcomes in the set, right? So what you need to understand is you can use a contingency table to calculate joint probabilities. That is intersection of events. You can also calculate marginal probabilities. That is single event. You can also test if 2 events are independent by using the product rule. We note that the rows and columns represent mutually exclusive, that is disjoint events. A1 has nothing to do with A2. B1 has nothing to do with B2. So they are mutually exclusive. That is A1 and A2 mutually exclusive, B1 and B2 mutually exclusive. Now, from the table, we can calculate the probability of A1, which means we say number of elements in A1, that is the total, which is A plus C, over number of possible outcomes. That is the N. That is what we refer to as the marginal probability. Then we can calculate the probability of B 2, right? That means how many elements are B2, C plus D over the possible outcomes, which is N. So again, this is the marginal probability, but this it is to do with the column and B2 to do with the row. Now, if we look at the probability of A2 intersection B1, right? We have our A2 intersection B1, that is what is common, right? Which is B. So B over the number of possible outcomes. And we call that joint probability because of this end thing, which is the intersection. Then we look at the probability of B2 given that A1 has occurred. Here already it is a conditional probability. We want the possibility of having our B2 given that A1 has already occurred. That means now we have reduced our sample space to A plus C, right? From the N, we are dealing with A plus 2 because A1 has occurred. Therefore, B2 is this one, given that already A1 has happened. So this is the intersection of that situation. So it will be C over A plus 2, which is now our new sample space. Now, let us look at this example here. The sports director at a school analyzed the data to determine how many learners play sport and what the gender of each learner is. The data is represented in the table below. You see, we have this data, but we have 4 variables: do not play sport, male and female, right? So that now, if you want to know the number of male that are in the school, you add 51 plus 49 to give you 120. If you want to find the number of female in the school, again, you add 49 and 7 to get 116, right? Fine. If you want to know how many students who do not play sport, that means you add 51 and 49 to get 100. Those who play sport, you add 69 and 67 to get 136. But now, if you want to know how many students are in the school, you could add the number of male and female. That should give you 236. Or you should add the number of those who play sports, that is 136, and those who do not play sport. Still, you get 236. This is important because some of this information of, say, how many students are in the school, it won't be given. But from the table, understanding the table, you can actually find those numbers. Now, what we need to do is to determine the probability that a learner selected at random is male, given that he plays sport, female, and plays sport. Then we go on to B, the events male and do not play sport, mutually exclusive. Use the values in the table to justify your answer. Then C, the events male and do not play sport, independent. Show all calculations to support your answer. Now, in questions of probability, it is always advisable that you define the variables. Like already I have said, there are 4. So you have to define those variables so that you can not always write the variable do not play sport as a statement as it is, but you need to define the variable that will represent the what? All the 4 variables that we have. So a solution to this, that is our starting point. Let S be the event play sport. Let S prime be the event do not play sport. M represent male, F represent female. Right now, once we have defined the variables or the letters that is going to represent the variables that we have, we then need to go back to the question, like Roman figure 1. male given that he plays sport. So we want to write this statement using symbols and also using the variables that we have already defined. So to do that, all what it means, we are saying the probability of male given that that male plays sports. That is what is being said here. And in symbol, we write it like this. This is the probability that we want to find. Then female and plays sport. That means we are simply going to say probability of female and S for sport. So this symbol represents this statement. Then we go to B. B is saying the events male and do not play sport mutually exclusive. Right? The next thing we need to ask ourselves is, when do we say events are mutually exclusive? Right? So that's the thing that we need to remember and write it down, so that when we are to answer B, we start by trying to show what we would have said in respect to when do we say events are mutually exclusive, right? So all what it means is, if we could show that the probability of male, right, for the male and do not play sport, that is S prime according to our definition, is equals to 0. All what it means is M and M prime, they don't have an intersection. We are writing this because we know that mutually exclusive events are events that are disjoint. That means they don't have an intersection. So if we are to find the probability of the intersection, we should get it as 0. When this is achieved, then we can actually conclude that the two events, men and do not play sports, is mutually exclusive. But if we get something different, then we conclude otherwise. Right? Then we go to C. Are the events male and do not play sports independent? Again, when do we say events are independent? Right? There are two things to that. Either if we could show that M intersection do not play sports, it's not an empty set, that means its probability is different from 0. Or we can show that the probability of M intersection S prime is the same as the product of their individual probabilities. That is the end rule. Then when this is satisfied, then we can safely say the events are independent. Otherwise, the events are not independent. And remember, the idea of saying mutually exclusive, the opposite of mutually exclusive is independent, right? And this is why we say, if we say events are non-mutually exclusive, we are simply saying they are independent, right? So if events that are mutually exclusive are disjoint, that means they don't have an intersection. So when we say they are independent, we mean they have an intersection. This is always right for one to know. It makes things clearer in a way that you don't end up confusing oneself. So having defined what we are supposed to give answers to, what is left now is to give solution to the problem. Right, the first one, Roman figure 1, probability of M given that S has occurred is equals to probability of M intersection S over probability of S. Remember here, the numerator, it is a fraction because probability is a fraction. The denominator, it is a fraction. So at times, be wise to substitute the division line by the actual division sign, because this numerator is being divided by this. So always substitute this with a division so that you don't confuse yourself, or your writing does not appear clumsy so that you end up confusing yourself. So the probability of M intersection S M is for men. Intersection S represents place spot. So we have 69. Out of how many students? 236. So the probability of the intersection is this one, divided by the probability of those who play spot is simply, how many are they? They are 136, right? Out of 236. This is the probability. Therefore, in such a case now, to simplify this, you change the division sign into a multiplication sign, but always remember to substitute this divisor by its reciprocal or inverse. That means the denominator becomes the numerator and the numerator becomes the denominator. That's the inverse of this, or this is inverse is this. Okay, then when you then simplify, you see that we have 69 over 136. That's the probability that it is a man, given that the person or the learner plays sports. Now we've got number, Roman figure 2, probability of female intersection plays sport. That means all what we need is female and plays sport. That is 67 over the total number of learners, which is 236, and that's the probability. Then are the events male and do not play sport mutually exclusive? We are supposed to use the values in the table to justify your answer. That means you cannot say yes, they are mutually exclusive without showing why are you saying yes or no. So to that, what we are simply going to do is we are saying if we could show that the probability of M and S prime is equal to 0, then we can safely conclude that M and S prime are mutually exclusive, right? So this is our hypothesis and our conclusion. So we work with the hypothesis. Once it is satisfied, then we can conclude that the two sets are mutually exclusive. So straight away, the probability of M and S prime, that is the men and do not play sports, is 51 over the total number of students, which is this probability. And this probability is not 0, that is different from 0. Therefore, the hypothesis was not satisfied. Therefore, we cannot conclude this, then we have to negate. Hence, events M and S prime are not mutually exclusive. Or by writing not mutually exclusive, could have said events M and S prime are independent, because you know that the opposite of mutually exclusive is independent events. Okay, right. Then you go to C. Are the events male and do not play sports independent? Show all calculations to support your answer. So you are not supposed to say yes or no if you don't show why you are saying that, right? We show that probability of M intersection S prime is equals to the product of their individual probability. That is probability of M times probability of S prime. That is, this is the multiplication or the end rule that we are applying, right? So if we are to find the probability of M intersection S prime is 51, that is M intersection do not play sport, 51 over 236, then we approximate that to 0.22. Then we find the probability of M, which is M, that is male, we have 51 plus 69 to give us 120. This is what we have here. Then we find the probability of do not play sports. Then you go to do not play sports, which is 51 plus 49, you get 100, which is 100 over 36. Right now, we are going to find the product of these two probabilities, right? So the product will mean I'll take 120 over 236 times 100 over 236. You discover that maybe you are questioning, why am I writing these numbers as decimal fraction? what normally happens at times, it won't be very clear that the fraction that you have as the probability here will be just the same as the fraction that you get as the probability. So when you see those things, try simply to write the probability as a decimal fraction to see whether you're going to get one and the same thing, right? So this is exactly why I've changed this to 0.22 and again change this to 0.22, because the fraction after you simplify here, you never get a same fraction as this. So for you to check whether are the two given probabilities the same, change them to a decimal fraction and you realize that surely they are equal. Right. So in such a case, since the probability of M intersection S prime is the same as the product of their individual probabilities, then M and S are independent events, or we can say M and S prime are non-mutually exclusive. It's one and the same thing. Okay, let's go to example number 2. The following contingency table gives data on the type of car grouped by petrol consumption owned by 100 people. Here we are told how many people are owning the cars in question, right? But they are grouped by petrol consumption, so that petrol consumption we have low, medium, and high. Right, we have female and men, isn't it? So that if you are to try to check of the 100 people, how many males do I have? You add 12 plus 33 plus 7. That should occupy this. How many females within the 100 people? You add 23 plus 21 plus 4. That is important. Then when it comes, how many cars that have low consumption, medium consumption, high consumption? Low, you add these two. High, you add these two. Median, you add these two. Okay? So in such a case, then what it means, when you look at this contingency table, we have 5 categorical variables, isn't it? Male, female, low, median, and high, right? So as continuation of the problem, I was simply explaining so that we understand the table, right? We are saying one person is selected at random, right? We let L be the event. The person owns a low rated car. So L corresponding to low rated car. F is the event, a female is chosen, right? So our task now is we want to find the probability, Roman figure 1, probability of low rated car. Then probability of female intersection low rated car, meaning that female or females, they use the low rated car, right? Then probability of female, given that the low rated car is where these females are, right? So giving solution to that, in this case, everything was defined for us, the variables, we don't need to define any. So first, probability of low rated car, you go to low rated car, then you need to add this column. How many are the low rated car? Then they are 35 over possible number of cars, that is 100. Because if we say we have 100 people with cars, so that means we have 100 cars, okay? So it will be 35 over 100, then you simplify to 7 over 20. Then we go to probability of female intersection low rated car. You go to female, then the low rated car, then it's 23 over number of people, hundreds, right? Then we go on to the probability of female, given that it's a low rated car. Already this is conditional probability, which is the same as probability of F intersection L over probability of L, which is what we have here. Then obviously this numerator is a probability on its own, that means it will be a fraction. So probability of the F intersection L, we have seen it already, is 23 over 100 divided by probability of L, which is 35 over 100. So substituting the bar by a division sign, we are saying 23 over 100 divided by 35 over 100. Then we convert the division into a multiplication sign. You see that this denominator is now a numerator. This numerator is now a denominator. Then you cross out, you see that it is 23 over 35. But one would say 23 is female and low-rated car, right? Over 35. So it means that if you actually understand the issue of conditional probability, that we are saying it reduces the sample space. The fact that the low-rated car is where we are working in. So that is our new sample space. So it will be female low-rated car, 23 over our new sample space, which is the addition of this to 35. So in short, I'm simply saying here we are given the car is low-rated. We want the total of that column, that is 12 plus 23, right, which is 35. Conditional probability reduces the sample space. So this is something that you need not to forget when it comes to conditional probability.